part 4 is again about this reduction of cholesterol, and we want to. There are different treatment groups. Right? So they're like a control group and light dosage group, medium dosage group, heavy dosage group. Right? So we want to see whether they're seeing different between the different treatments, and there's a control which is didn't receive any treatment. Right? So there is a parametric test for this, is parametric F test, right? It's one way ANOVA F test for testing whether they're seeing any difference between the average results from the 4 different groups, right? So the null hypothesis is what? There's no significant difference in average reduction in LDL among the 4 treatment groups. Or 4 treatment populations, right? And of course, the alternative is there is significant difference in average reduction, in average reduction of okay. Some students like to say mu1, mu2, mu2, and say mu1 equal to mu2 equal to mu3 equal to mu4 for now, and then say mu1 not equal to mu2, not equal to mu3. The null is good, but the alternative is not good, right? The alternative hypothesis is just some different exists, maybe among 2, among 3, or maybe they're all different, okay? It all satisfies the alternative. So it could be just a treatment 1 and treatment group different is significant, the rest of them, right? They're all the same as second treatment or first treatment, right? Don't say they're all different from each other. That's not a true statement, right statement to use. Okay. Then you will have to test this hypothesis, and the setup of this will be similar to the setup for the 2 independent sample tests. You need to have 2 closest. You need to have 2 variables. One is for the scores or reduction, and the other one is for group, right? So it'd be similar to this one. Right? Well, unfortunately, I need to do this again, right? So, not unfortunately, right? But it shouldn't be too bad. Hold on. Wrong thing. Whoa. Create another data. Okay, this time called data set 4. Okay. Then I have 20. And another variable, so I have a group variable. Then I have a reduction. Oops. Okay, that's good. Make it bigger. Okay, then so I have our data entered. Okay, I think so. This is important, right? Don't put in 4 columns, and you're not going to be able to get this. Put in 4 columns, that becomes repeat the measurement design. That's a different design. Okay, so click OK. In fact, to do a proper study, we need to check normality assumption and equivariance assumption. But since my first question asking for to do the hypothesis test, right? So let's do the hypothesis test first. So we're going to click statistic, means. Oh, I can do that, right? Why? Because that group variable is not factor, right? So you do data, manage variable active data set. So same thing as you do with two independent sample tests. I like the group variable. I'm going to use a number. I don't want to waste my time, right? Especially when you do the exam, you don't want to do that, right? Just check use number, and then don't specify a new variable. Just replace it with the number. So now this variable, group variable, becomes a factor variable now. Then you can do the analysis. So click statistic, means, one-way ANOVA. Right now it's variable because you have a factor variable now. Now, if you wish to do pairwise comparison, I didn't do that. Right? You can do pairwise comparison. And watch this. There's a Welch F statistic not assuming equivariance. So in case you do really have non-equal variance situation, you can check on this to do your test. Right? I'm going to click on pairwise comparison and run it again. The first time we run, maybe let's just skip this. First time we run, there. Let me cancel this. Did I run it? I think I ran it, right? Oh no, I didn't run it. Okay, so I thought I ran it. So click it. I ran the model one time, was earlier for two independent sample tests for checking normality. I ran it, I remember that. So one-way ANOVA. So I have this model 2, 3 for this one, and pairwise comparisons. I want to have them all together, all around. So click OK. So I have this a nice graph, right? So we have this first ANOVA test. This is ANOVA table, right? And also variance model. This is model 2. This number underneath that is the p-value, right? And the F statistic is 12.55, okay? And the p-value is very small. So we'll go back to the F statistic. Actually is this. P-value is this. F statistic is pretty high, p-value is small, so you can conclude your analysis, right? Report p-value of F-test and conclusion. So I'm going to skip the typing, right? You know how to write it, right? Reject the null hypothesis because the p-value is less than 0.05, right? And so you're going to say there's sufficient evidence to support the alternative hypothesis that there's significant difference, statistically, there's significant different amount of mean. You don't know where the significance is, right? Lies, but you do know there's some significant difference among the mean. Okay. And you want to verify the assumption of F statistic, and then you will go back. You ran the regression model, you can click it. Actually, ANOVA is a regression model. Right? You're going to do regression later on, so I mentioned that regression term, but we did this. So you can do this numeric diagnostic, right? To look at heteroscedasticity. That means equivariance. That's another way to say equivariance. Right? You can do that, right? So you can test that, right? And just use a regular setting. There is a p-value, right? For brush Hagen test, right? 0.3, that's higher than 0.05, so equivariance is good, right? Then click model graphs. You can look at the basic diagnostic graph, okay? It'll be behind. So you see that's a normality test, QQ plot. So that's good enough, right? That's good enough. I think I showed that in my video too, right? So that's good enough. So you can actually, if you want to, copy clipboard, and so to support your results. Oops. No, I didn't get it. Okay. So you get this picture, and make it smaller. And I didn't copy the test of equality of variance. So that's need to be somewhere there, right? I'm sorry about this. So this is for test of equality of variance. And I think you know how to draw a conclusion, right? This F test, this test for equality of variance, P value for test of equality of variance is not less than 0.05. The equivariance assumption is acceptable. The normality assumption is also acceptable since the normal QQ plot something like the data point form a straight line pattern. Okay. Straight line pattern means all the dots follow straight line pattern. If you have one dot down here, right, that's not straight line pattern anymore. One or two dots out of that straight line, that's not good, right? That means you have extreme value, which is not good. Okay. Cool. Then, of course, when you run that analysis, you will see a lot of other output. Go back, right? You have these two keys contrast, right? Two keys contrast. Let me see. Report the mean and standard deviation for you, then actually give you the t-test for comparing these group pairwise. Group 1 and group 2, difference not significant. Group 3 and group 1 significant. So you see these asterisks, 2 or 3 or 1, that actually tell you how significant those differences. Right? 1 generally means less than 0.05. 2 means what? Less than 0.01. Okay, and then 3 means less than 0.001. Okay, so this actually gives you the hypothesis test for all the pairs, right? Pairs of groups. Then also report to you the confidence interval estimate for difference between pairs. And the bottom one tell you the subgrouping, right? 1 and 2, they all label it as A. That means what? This 1 and 2, group 1 and group 2 is within one, so they call it homogeneous subset, right? Within subset, the difference is not significant. 3 and 4 form a homogeneous subset, right? So difference between 3 and 4 is not significant. But 1 and 2, 3 and 4, these two subsets, the difference is significant. So they're separate. Okay. So in this, it is kind of like evaluating the performance of these drugs for reducing cholesterol, right? So you will see the control group and treatment group. First treatment group difference is not significant. So that first treatment level dosage is not quite good, right? But the third, and actually I should say, the medium dosage and heavy dosage, right? They're different from control group. Their improvement is, or reduction is much higher. Right? So it really depends, right? If there's some side effect from these drugs, then probably if the medium dosage and heavy dosage give you the similar type of result, you probably would consider using the medium dosage instead of higher dosage. Okay. But here it's showing you the medium dosage and heavy dosage, the difference is not significant. Okay. So that's actually part C, and I want to. So that's it. Huh? So what you can do, either way, here I ask you to do multiple comparison using to see what the difference is, and also identify homogeneous subset. Right? So you can actually just, well, use all these information if you want, right? Linear contrast, or family confidence interval, or just the confidence interval, right? Be good enough. If you know how to interpret these confidence intervals. If you're not sure, a lot of people actually like to use the test, right? Testing significance. Right? So let me put that down here. Let me shift it in. Try to use a difference. Okay. So in my lecture, I also mentioned so-called a family-wise type 1 error. Okay. When we do the test, if you really try to compare these 6 tests, every time you do the test, you use 5% level of significance to do the test, then you're using too many, your chance of committing type 1 error will be increased, right? So oftentimes people suggest that we should use so-called a family-wise type 1 error rate, right? In the process, you really need to compare them 6 times, do 6 tests altogether. What we should do is, if overall alpha is 5%, we should divide that 5% by 6. So you get like 0.0008 or something like that, right? Almost very close to 0.01. And then compare this p-value with those values, right? So this one, actually, we're lucky actually, this one actually is 0.02, right? This 0.02, if you use a family-wise type 1 error rate, that means you're going to divide that 5% by 6 to get the type 1 error rate you should use for each test. Then that is less than 0.01, right? So the cutoff p-value should be 0.01. Now you have a 0.02, which is higher than 0.01. So if you want to use a family-wise type 1 error rate, this one would not be significant enough. Am I making sense? Okay. So the bottom one, they actually use a 95% family-wise confidence interval. That means when they calculate this confidence interval, they already factor in that overall confidence level to be keeping 95%. So when they're calculating these confidence interval, they are not using 95% confidence level, right, to get the t-score and calculate this confidence interval. I hope I'm making sense, right? So the overall confidence level in this case is 95%. They adjust those alpha when they're calculating the confidence interval. So hope that makes sense, right? And over here, of course, you can make the decision. They give you the p-value of the test. You can decide whether you want to use a family-wise type 1 error or not. Okay. This is we call it so-called a post-hoc analysis. When you run one-way ANOVA, in the beginning, you don't really have a clue which pair you want to compare. So you want to do all the comparison, right? While you're doing this, and you want to compare all 6 pairs. There are only 6 possible comparisons you can do if you have 4 treatment groups. In that case, your alpha should be divided by 6, right, for each of those tests in order to achieve so-called family-wise type 1 error maintained at 5%. Okay, so that's a kind of important thing that you need to know. Okay, just in case in the future you involve in certain study and then people mention that, you understand what it means. Okay, and this is one test. 2T's method is one test. There's so many different multiple comparison methods out there. Okay. In my other class, I actually introduced maybe 6 or 7 of them, right? But this class, I don't think we have to worry about. You got the idea, right? That you can do these multiple comparison. Now, different methods will give you different size of the interval. So, hope you know that, right? So while you're running these different methods for multiple comparison, you find out that, well, the results are different. Well, because the different methods, some are more conservative, some are less conservative, so you tend to get different results.